Hello, I'm Jim Burnett, bringing you this 8th program in our series, NASA and Aeronautics. In this program, we take a look at the future and what it holds in store for NASA. We also take a look back at some past aeronautical accomplishments. However, right now, our series takes us to January of 1978. This film deals with researchers who are conducting tests in hope of extending the lifespan of aircraft tires.
Scenes like this are repeated thousands of times daily at busy metropolitan airports throughout the country. Again and again, aircraft tires touch down, brakes are applied, the plane taxis, and takes off once more. Keeping a fleet of planes and tires is a definite economic problem, since the lifetime of a tire tread can range from 300 takeoff and landing cycles all the way down to 10 or 15, depending on the aircraft and the nature of its operations. One airline uses more than 700 tires a month, just on its 727 jets, and that's only half its fleet. In contrast to automobile tires, aircraft tires are retreaded 5 or 6 times before being scrapped, mainly because the tire body does not deteriorate as quickly as the tread does. 7 years ago, chemists at NASA's Ames Research Center in California began working on a new synthetic rubber, an effort to increase the safety and durability of aircraft tires. Here at the Thompson Tire and Rubber Company in San Francisco, technicians retreaded a number of aircraft tires with a NASA compound. By using an experimental polymer, the chemists were able to create a rubber compound with different physical properties that give the tread both strength and longevity, an ideal combination for aircraft tires. First stop for the newly fabricated tires after the successful laboratory test, high-speed dynamometer qualifications. Taxi, takeoffs, even aborted takeoffs can be simulated. To qualify a tire for use on an airplane, it must pass 150 of these rigorous cycles. And the pre-flight testing doesn't stop there. To find out if the tires had any wear or traction deficiencies, they were repeatedly put to the test at the Langley Research Center's landing loads track. Tires can be exposed to braking, including locked wheel skids, and tested on both dry and flooded concrete runway surfaces at speeds up to 100 knots. With help from the FAA Aeronautical Center at Oklahoma City, the new polymer tire moved through another research step. For these tests, tires with experimental rubber were installed on the inboard wheel of one landing gear of a 727 jet and the outboard wheel of the other. For comparison, they mounted standard tires on the remaining wheels. Periodically taken tread depth measurements help to determine the extent of tread wear. Now the research has moved full circle. At their maintenance hangar in Miami, Eastern Airlines mechanics mounted the fully certified NASA polymer tires side by side with their standard tires. Initial findings show the new polymer compound's wear performance is better than conventional tires, and the results look very promising. This NASA research is part of a continuing effort aimed at seeking new materials to improve aircraft tire tread wear, traction, and blowout resistance. and ultimately to improve the safety and economy of aircraft ground operations.
Now we see a film that illustrates NASA's concern with improving the techniques of crop dusting. This type of research is important since a large portion of worldwide crops are lost each year to pests.
Small crop spraying aircraft like this have made significant contributions to this country's ability to produce food. The National Science Foundation estimates that more than 1/3 of worldwide crops are lost each year to various pests. As of last year, some 8,600 fixed and rotary wing aircraft dispensed insecticides as well as seeds and fertilizers over 180 million acres of croplands in the U.S. alone. Although the aircraft themselves have improved, they still use applications technology developed in the 1940s. Now, NASA is involved in a research effort using full-scale wind tunnels and other facilities in an attempt to solve some of the problems that crop dusting pilots have faced for years. Dr. Bruce Holmes, in the Flight Research Division at NASA's Langley Research Center, is manager of the program.
We're studying several different areas, different aspects of the aerial application industry problems. These areas include studies of airplane wakes and how materials are affected in this, how sprays, for example, are affected in the wake behind the airplane. We're also studying airplane aerodynamics and handling qualities characteristics to try and improve handling qualities and fuel efficiency, as well as overall airplane performance. We're also studying the dispersal systems and how they perform, both liquid and dry systems. In addition, we would like to look for better ways to measure spray patterns from airplanes. All of these areas of work, we hope, will lead to both near-term solutions to some of the existing problems I've described, as well as provide airplane designers in the future with better techniques for designing airplanes that are specifically suited for aerial applications work.
At the Vortex Research Facility, engineers study the swirling patterns of air that trail along behind the aircraft. Because these air currents affect the uniformity of application and cause chemicals to drift during spraying, they are prime targets for improvement. Researchers are hopeful they can make the vortices work for them as the plane flies along. Loading the scale model with polystyrene or glass beads, then applying double-sided tape to the floor, researchers can simulate spray patterns by actually counting the particles that stick to the tape. In addition to the full-scale tunnel and vortex facility work, promising concepts coming out of that research will become part of actual flight tests in the near future. From these will come important pilot comments, as well as a chance to measure effects on dispersal patterns and overall airplane performance. Research on crop dusters, aircraft that fly as close as possible to Earth to increase agricultural productivity.
This next film we watch is about winglets. Winglets are devices that are added to planes to cut down fuel consumption. They can be useful in saving dollars as well as helping preserve some of our petroleum resources.
The 3.5-foot high vertical fins added to the wingtips of this Learjet are intended to cut down drag on the plane as it moves through the air, reducing fuel consumption at the same time. They're called winglets. Dr. Richard T. Whitcomb of NASA's Langley Research Center in Virginia is the winglets engineer-inventor.
The flow around the wingtip is such that the air is moving inward here and outward here. When we put the winglet on, this stops or reduces the flow into the wingtip above the upper surface of the wing, and as a result, reduces the vortex strength downstream. It's interesting to note that because this little wing-like device is in a crossflow, it acts like a sailboat tacking upwind. There is a force forward on the winglet just as there is on a sailboat. And it's this that reduces the drag. This device has now been applied to several airplanes.
After the basic idea for winglets was developed, the theory was put to the test using wind tunnel models like this. Since the theory has been verified, the wind tunnel tests are now primarily investigating winglets for different applications. These include placing winglets on an Air Force KC-135 jet cargo tanker. The expected 8% improvement in performance could result in an annual fuel savings of 45 million gallons for the fleet. Dr. Whitcomb, the winglets inventor, believes the new concept can be applied to existing aircraft, ranging from commercial transports to business jets and even smaller general aviation airplanes. Winglets are also being installed on agricultural-type aircraft used to spray insecticides and other materials on crops. The winglets are expected to allow a much smoother and more uniform swath as the chemicals are applied to the crops. The place is a research and development facility at the Mojave Airport in California, and this is the Very Easy, a small two-place cross-country type airplane made for the home-built market. There are several hundred of these being constructed in people's garages around the world. It, too, uses the NASA-developed winglets to improve the airplane, according to designer Bert Rutan.
The airplane's cruise efficiency is approximately equivalent to adding another 5% of range, or getting 5% less fuel used to go the same distance because of the use of the NASA winglets.
Winglets, devices that can be added to existing airplanes to reduce the amount of fuel needed.
Now we turn our attention to a series of aircraft spin tests conducted by NASA. This research is helpful for improving spin qualities in existing planes, as well as planes that are still in their early design stages.
For men like Wayne Lee, Bill Mims, and the rest of the ground crew, it's a job they've done many times in the past. Even so, it's a job they don't rush to finish. Above all, what they do is thorough. The data that will be gathered in today's test flight and safety of the man who will fly the plane are dependent on how well they prepare the plane and its instrumentation for flight. The place is NASA's Wallops Island, Virginia. The plane the ground crew has been working on since 5:30 a.m. is a typical general aviation light aircraft. And this is the man who will fly it, 50-year-old engineering research pilot Jim Patton. When Jim Patton takes the plane up for a spin, that's exactly what he'll be doing, making the plane spin on purpose. The research is being done because about 30% of all general aviation fatalities can be traced to stall spin problems. Repeatedly, Patton noses the aircraft skyward till the small plane stalls. It then pitches over, and the spins begin.
2, 3, 4. Seems to be staying fairly steep. 5, 6. Stable. 7. Recovering, and it's responding slowly.
A typical flight lasts about an hour and a half.
Okay, recovered. Phase 1. Nose rails a little bit.
Occasionally, when he can't recover from a spin, a parachute mounted in the tail is popped to stabilize the spinning plane.
Jettison. 2 events. There's 2.
Much of the data that may one day help researchers find better ways to design stall-proof aircraft returns to this telemetry station on the ground. Here, Paul Stow and his team of engineers monitor and record results of the day's spins. Research pilot Jim Patton pointed out some of the many modifications that have been tested on the plane.
This aft fuselage strake, the so-called soda straws under the edges of the fuselage, and the fairing back here, which acts as a ventral, were all sized and located on the airplane in the spin tunnel on models. And we investigate these singly and in combination in full-scale flight.
The full-scale testing is only one part of the overall effort. At the Langley Research Center, engineers test models in a spin tunnel and several other wind tunnel facilities there. On an unused runway in West Point, Virginia, south of Richmond, another group of Langley engineers and technicians fly radio-controlled models of the same general aviation plane. Results of these tests are correlated with results from both the spin tunnel studies and the full-scale flight tests. Stall spin research, an intensive program aimed at improving stall and spin characteristics of both presently flying aircraft and for planes designed in the future.
4, pretty stabilized, still spinning up. 5.
In this next film, we examine some of the advances that NASA has made in the area of avionics. Avionics are the electronic systems in aircraft that provide communication and flight data and control. The strides made in avionics are important in raising the standards of performance and safety.
545, you call us up. 545. No, 702, what's your plan, sir?
The electronic systems in aircraft that help pilots communicate with the ground and provide navigation, guidance, and flight control are called avionics. By taking advantage of advances in electronics and microcomputers, the ease and safety of flying in the future may be greatly enhanced. One of the places involved in advanced avionics studies is NASA's Ames Research Center in California.
Right now, the pilot, and in particular the sportsman pilot, has a lot of things to do. And he's the navigator, he's the pilot, he's the crew chief. He has to load the aircraft properly and so forth. So the thought is that the computer could do a lot of this work and let the pilot be free from making decisions and gathering information. For example, information on the weather. He can concentrate on important decisions.
Using a small computer and television screen that's sensitive to touch, like some of today's calculators, the pilot is assisted with a variety of tasks, including loading the plane.
On the screen you see a simplified photograph, or I should say a top view schematic of the aircraft, a diagram in the lower left-hand corner which represents the forward safe limit of the balance point and the aft safe limit, as well as the maximum weight of the aircraft. So that's, in a sense, a safety diagram. Of course, I load it physically by putting the objects in the aircraft, but here I go through the procedure of touching the screen to represent those objects in the aircraft. These are people, fuel, baggage or cargo, and so forth.
The computer requests the weight of the co-pilot, for example, and an X flashes where the co-pilot's seat is.
Enter co-pilot weight.
184.
184 pounds, and I touch go. Then notice that you have voice feedback, or echo back as we call it. I don't have to look at the screen all the time to see if that number is entered correctly. I can hear it come back to me. So in a sense, it's a check on accuracy. Okay, after entering that number, I touch go to actually insert it in the computer.
Once the television monitor, computer, and voice synthesizer are installed in the aircraft, it will be possible to use them for navigation, guidance, and plotting the flight. Again, aerospace engineer Chuck Jackson.
In the center panel of the instrument panel, we have a fixed map, but this is where the television monitor would be. So for the moment, we'll work with this fixed map and give you an idea of how we might plan a flight. Let's say, for example, we want to fly from San Jose, California to Livermore, California by way of Hayward and Calaveras Reservoir. By the way, this replaces the idea of spreading charts out over the kitchen table, drawing lines, measuring courses and distances, and all the details that normally go with intelligently planning a flight. Here you can do it right in the airplane more accurately and more simply by simply pointing to what you want. Okay, the pen is positioned at San Jose and it asks what altitude I want there. Well, if I'm going to take off, I'll say 0 feet.
0.
And go.
Go.
Now the pen moves to Hayward. Let's say we want to make a low pass at 1,000 feet.
With an advanced avionics system, the computer tunes the navigation radios and points out the plane's location on the map. So you're never lost, a tremendous asset to safety.
600 or 3,600 feet.
3,600.
And go.
Go.
For our final film, we return to the subject of the X-15. This is a project that had been terminated in 1969. The film is a nostalgic look back on the importance of the X-15 in the 1960s and the effect it has on aircraft research in 1980.
There were 12 in all, men like Bill Dana, Milt Thompson, Pete Knight, John McKay, Joe Engel, and Bob Rushworth. They shared a common occupation, test pilot. For 9 years, these pilots flew the rocket-powered X-15 research airplane. 199 flights were made, many along the fringes of space. It was 20 years ago that the X-15, now hanging in the National Air and Space Museum in Washington, made its first research flight. NASA astronaut Joe Engel, who piloted the X-15 16 times, talked about the super-fast rocket plane.
The wings, of course, are very small. At the high velocities and high speeds that are obtained, you don't need a lot of lifting surface. And so lifting surface wings generally mean drag, and the desire was to keep the drag as low as possible. The airplane was made out of Inconel X steel. The skin was Inconel steel, which was a material that would resist heat up to about 1,200 degrees. That, incidentally, was the temperature that the airplane had to accept at Mach 6. The aerodynamic heating at 4,000 miles an hour got up to 1,200 degrees. Aluminum is not able to withstand those temperatures and retain any kind of strength. So the skin of the airplane had to be steel instead of aluminum. In subsequent flights, when the airplane went even faster, even the Inconel steel had to be coated with a protective material to keep the temperature, the surface temperature, from getting to the skin and getting hotter than what even the Inconel X could withstand. The most prominent feature, probably from where we're standing, is the rocket engine on the back end. It's a 60,000-pound thrust engine, liquid propelled. All the propellant was carried in the fuselage, and looking at the airplane from this angle, you can see the bubble, the cockpit bubble up toward the front end of the airplane. Just about the entire fuselage aft of the cockpit was fuel tank for propellant for the rocket engine. That propellant would burn out in 80, 88, 89 seconds.
Traveling at speeds in excess of 4,500 miles per hour, the X-15 climbed to altitudes of over 67 miles, qualifying pilots for astronaut wings before the first man flew into space. The highly successful program returned large amounts of data about structures and heat transfer, and proved that man could fly at hypersonic speeds and adjust to control systems that are part of NASA's new space shuttle. Astronaut Joe Engel is scheduled to pilot the second shuttle orbiter into space.
The techniques and flight control systems, the manner in which we fly of maneuvering re-entry from space back into the atmosphere, manage the energy, terminating in a conventional landing on a lake bed now, but eventually on a runway. That technique that we're using on the space shuttle was pioneered and in fact very similar to the same technique that we used on the X-15 20 years ago. We've got that knowledge and know-how and the confidence to do it.
The X-15, forerunner of today's spacecraft and tomorrow's airplane.
What we now have is a confirmation of the advances from NASA's research. By referring to the past and looking ahead to the future, we get a clear understanding of aeronautical progress. Next week, our program is built around a series of films made in the early 1980s. The show is called Setting the Stage for the Future. Till next week, I'm Jim Burnett.